All right, we have been talking about entropy and the second law of thermodynamics. And we've seen that the second law is at the core of what it means to even achieve an equilibrium state, and that the condition that entropy be a maximum at the equilibrium state means that things will move towards higher states of entropy. We saw earlier why that's so. Statistics is at the base of it. We've done a bunch of calculations on essentially mechanical systems, but we haven't yet talked about chemical reactions, and chemical reactions are, of course, by far the most important thing for chemists. So now we shift gears a little bit to talk about the entropy change for a chemical reaction. So let's consider this generic or very common chemical reaction. 2 hydrogens plus an oxygen form 2 waters. What do we mean when we talk about the entropy change for a chemical reaction like that? Well, there's 2 parts to it, of course, as always. There's the entropy change inside the system itself, an entropy of the system, a delta S of the system. And then there's an entropy change for the surroundings, and those two are very different things. And it's not obvious from the way many textbooks talk about it that they are different things, so let's be careful at this point. Usually a chemical reaction like this takes place at constant temperature and constant pressure, and even if I don't say so, I'm going to be assuming constant temperature, constant pressure conditions for the next little time. Unless there's some reason why it's not constant temperature or constant pressure. All right, so what's going on in this chemical reaction is that you're starting with 2 molecules of hydrogen, diatomic molecule, 1 molecule of oxygen, also a diatomic molecule but with a double bond. And out on the other side, you're getting 2 molecules of water, both of which are 3 atom molecules and have 2 hydrogen-oxygen bonds. So we're trading 2 HH bonds over here and an OO double bond over here for 4 H oxygen bonds. And in the course of doing that, lots of things change. Of course, the bonding energy changes, but it turns out that the bonding energy doesn't contribute to the delta S of the system. It contributes to the delta S of the surroundings, but not to the delta S of the system. The things that contribute to the delta S of the system are the intrinsic entropies of these molecules. So it's the rotations that they can undergo. 2 molecules of hydrogen can rotate over here, plus a molecule of oxygen. 2 molecules of water can rotate over here, but notice that there's 3 moles of stuff that's rotating over here and only 2 moles of stuff that's rotating over there. So there's more rotational freedom on the reactant side than there is on the product side. Likewise for translations, the molecules can all move in space, but there's 3 moles of them, and those translational motions, of course, are degrees of freedom. They contribute to the total number of microstates available to the system, same for the rotations. But there's 3 moles of molecules that can move on the reactant side and only 2 moles that can translate or rotate on the product side. There's also vibrations. They don't contribute very much to the entropy, but they are there and they do change. There are 3 total vibrators. On this side, right, there's a vibrator for each of these 2 molecules plus a vibrator for the oxygen. And it isn't obvious, but there are 3 vibrators for this molecule and also 3 vibrators for that molecule. So there's a total of 6 vibrations on the other side. So vibrations are going to contribute contribute a greater amount of entropy on the product side than on the reactant side, but the vibrational contributions are rather small. So overall, just looking at the molecules, and especially at how many moles there are on the 2 sides, we are going to expect that the delta S of the system, the quantity we're actually going to calculate from thermodynamic tables, should be negative. We should lose entropy in the system itself in going from the products to the from the reactants to the products. We know, however, that this reaction goes spontaneously, and in fact goes very strongly spontaneously. This is the reaction that leads to, explosive situations. If you mix hydrogen and oxygen and touch them off, and if the mixture is right, you can blow up a city with this reaction. So it's a very favorable chemical reaction. That's despite the fact that the system entropy itself is small. And that means that the surroundings entropy must be large and favorable, and we'll see that it is. From thermodynamic tables, we can get values of the entropies, the intrinsic entropies, for each of these molecules. These are entropies per mole, which means that since there's 2 moles of hydrogen here, we have to multiply by 2. And 1 mole of oxygen here, multiply by 1. 2 moles of water, so multiply by 2. Minus signs on the reactants, a plus sign on the products. The rule is that the delta S of reaction is the delta S for, or the entropy for the products minus the entropy for the reactants, right? It's always final state, and that's the products, minus the initial state, and that's the reactants, weighted by stoichiometric coefficients, and that just means multiply by, the stoichiometric coefficients here that are present on every species. And so it's 2 times the entropy for water minus a quantity 2 times the entropy for hydrogen plus the entropy for oxygen. That's the quantity that we're going to calculate when we're taking numbers from the thermodynamic tables for entropy. Let's look at the other contribution, though, the contribution to the surroundings. We've just looked at the contribution for the system itself so far. For the surroundings, the contribution will be Q over T, right? Let's suppose there's a T bath out here, as always. It'll be Q over T, and Q will be the amount of heat energy released to the surroundings if we're at constant pressure conditions. That's a QP. Q at constant pressure, and that QP is a delta H, right? Delta H, the whole reason for inventing delta H in the first place is that it makes it easier to calculate heat changes under constant pressure conditions. And it'll have a minus sign because this is the delta H, this is the heat lost by the system, but that's minus the heat gained by the surroundings. So if we want the entropy change for the surroundings, we need a minus sign there. And then we divide by T because the temperature is not changing, so we don't even need to do an integral in this case. All right. That means that when the reaction takes place, what we want to look at is how much heat is released, and the heat released is mainly going to be bond energy changes. Now, it isn't exclusively that. There are some other small contributions, but mostly it's bond energy, which means that we're going to look at how much energy it takes to break the 2 hydrogen-hydrogen bonds, how much energy it takes to break the oxygen-oxygen bond. Both of those are energies we have to put in, right? If those were the only energies, we'd have to be putting energy in from the surroundings, not losing energy out to the surroundings. So those are unfavorable contributions to the overall chemical reaction. But we're going to gain 4 HO bonds on the other side. All those bond energies or enthalpies are represented by, again, numbers from the thermodynamic tables. We'll talk more about these numbers from the tables in just a second, but because they do need some commenting. But for the moment, the rule for calculating the overall delta H of reaction, you guys have probably seen this since freshman chemistry, probably several times since too, so this should all be familiar, is the number of waters times the delta H for waters, the number of hydrogens times the delta H for hydrogens, and then the delta H for oxygen with a minus sign for all the reactants, a plus sign for the products. So again, it's products minus reactants weighted by stoichiometric coefficients. Okay, so now we've looked at both contributions to the entropy change for this chemical reaction. What's the total delta S? Well, it's going to be the delta S for the system plus the delta S for the surroundings. That's the delta S for the system minus delta H for the system, right? This number is actually delta H for the system. The minus sign is because it should be delta H for the surroundings at constant temperature and pressure. And that means that if I multiply, and that's the total delta S, and what we're going to find out is that this term is the one that dominates, so we're going to get, and this delta H is going to be a negative quantity, so we're going to get an overall delta S total that's positive, in keeping with the fact that we know this is a spontaneous chemical reaction. This is a very spontaneous chemical reaction. We're seeing that the heat release to the surroundings, in this case, is the dominant term. The entropy changes in the molecules themselves are swamped by the huge amount of energy that's dumped out into the surroundings and increases the entropy of the surroundings. And so the overall total entropy change is going to be positive and favorable, and that's going to be due to the loss of heat to the surroundings or energy to the surroundings. However, just jumping ahead a little bit, let's suppose we take this total entropy change for system and surroundings and we multiply by minus T. So that's what I've done here. Multiplied this thing by minus T. Then you can see that the quantity I get is delta H minus T delta S. Is that familiar to people? It should sound familiar from other classes, especially freshman chemistry. That's the Gibbs free energy. And so before we even get to the Gibbs free energy, we'll talk about this separately and on its own later, but even before we get to the Gibbs free energy, just looking at the total entropy change today, we've seen why we want to even talk about Gibbs free energy. It turns out to be that for a constant temperature, constant pressure process like this, for any constant temperature, constant pressure process, the Gibbs free energy is just a proxy. It's a stand-in for the total entropy change in both system and surroundings. It's a convenient way for dealing with both system and surroundings at once without having to think about it too hard. And we'll, like I say, we'll come back to that. Gibbs free energy is really key, of course, for all of chemistry. All right, so let's do an example. Let's suppose I have this reaction. I've got 2 carbon dioxides plus some hydrogen. I'm going to reduce the carbon dioxide, form a formaldehyde, and I'll have a leftover oxygen molecule. From the tables that you can find on the internet and in other textbooks and stuff, the entropy, the standard absolute third law entropy, which we'll talk about what that means in a minute, is 213.74 for the CO2, 130.68 for the H2, 218.8 for the formaldehyde, and 205.14 for the O2. Using our products minus reactants rule, it's 2 times the CO2 plus 1 sorry, I take that back. Those are the reactants. 2 times the formaldehyde plus 1 times the oxygen minus 2 times the CO2 minus the quantity 2 times CO2 plus 2 times the hydrogen, and that gives it a total of minus 46.1 joules per K per mole. Let's look at that number and see if we can make at least a little bit of sense out of it. After you get some experience with these, you can start getting a feeling for how big, you can look at the chemical reaction and get a feeling for how big the number should be coming out, or at least a rough feeling. But to get just a start on that, let's look at one salient feature, and that is that there's 4 moles of gas on this side, and there's only 3 moles of gas on this side. So the fact that this came out negative, the fact that the delta S for the system itself is actually unfavorable is not surprising. Just looking at how many moles we have, and the fact that they're all gases, right? No liquids here, doesn't surprise us that we get a negative number. Let's suppose that one of these had been a liquid. Let's suppose the CO2 had been a liquid, for example. Would that change the calculation? Well, yes. Gases have much higher intrinsic entropies than liquids do, or if it were a solid, even more so. And so when you're looking at how many moles there are on both sides and deciding whether you expect a negative or positive entropy change on the basis of that, you also got to look at whether you're comparing gases to gases on the 2 sides, or whether you're comparing gases to liquids or something like that. All right, let's talk about this third law. The third law of thermodynamics. I think this is a little bit of a misnomer. It's really not as important a fact, at least in my opinion, as the title third law seems to imply. It's the last of the three laws of thermodynamics that was formulated. It wasn't formulated, I think, till the early 20th century. Most of thermodynamics is from the middle of the 19th century. But it is useful and important in this particular context especially. The entries that you see in the tables are not delta S's. Everything else you'll see, delta H's and delta G's and so on, have a little delta in front of them, but these are not delta S's. These are absolute entropies. And the reason they're absolute entropies is because they're calculated using the third law of thermodynamics. And what the third law says is that the entropy of a perfect crystal at zero temperature, no thermal energy whatsoever, is zero. In other words, the entropy has its own natural zero point. And these entries in the table have been calculated using that 0 Kelvin state of being as their reference point. They are delta S's in a sense, but they're delta S's from a natural zero. And so in that sense, they're not delta S's, they're absolute entropies. So what is the third law really saying here? Well, from the statistical point of view, if I freeze a system all the way down to 0 K, and everything's got to be a crystal at that point, right? There are no gases at 0 K. And if there's no imperfections in the crystal, no defects, no impurities or anything like that, then every single atom, every single molecule has only one possible position, one possible orientation, and it's not vibrating, and nothing else is going. It's not undergoing internal quantum transitions or anything like that. And that means there's only one microstate available to the whole dang crystal. Everything is locked in place. That one locked arrangement is the only microstate that the system can take on. And that means if we use our Boltzmann relationship here to calculate what the entropy is, we're going to get a log of 1, and that gives us 0. So what's really going on is that all the degrees of freedom and all the microstates that are normally available to a system at a finite temperature are just frozen out. And that's why the entropy is 0 at absolute 0. This law was formulated at a time when the statistical interpretation of thermodynamics was beginning to be appreciated. It wasn't fully appreciated yet, but it was post-Boltzmann. Boltzmann was already, this relationship already was known, I think anyway, if I have the history right in my own mind. This relationship was already known when the third law was formulated. So third law is formulated without reference to the statistics, as all of thermodynamics is, but it isn't quite, a pure work of logical genius the way the second law of thermodynamics was, which was formulated without any understanding of or knowledge of the statistical underpinnings of thermo. All right. So that's all great. That means if we have a set of thermodynamic tables, we can calculate delta H's and delta S's. And we will see that that's absolutely central to understand. Well, I think everybody knows already that those things are absolutely central to understanding when you'll get chemical equilibrium, when you won't, how far you are from chemical equilibrium, whether a chemical reaction will go forward or not, whether a chemical reaction will release heat or not, or absorb heat, all these crucial things that are necessary to understand what's going to happen when your chemical reaction tries to go, at least, whether it'll go forward or backward, all these kinds of issues. But the tables are all tabulated for some fixed reference temperature. It's usually 298. It doesn't have to be, but it's almost always 298 K. That's the standard, by far the most common case. And you're never in real life probably gonna encounter a situation where you're exactly at 298 K, right? You're always going to be at least a little bit off. 298 K is nice because it's near room temperature, so it's going to be pretty close to most of the situations you encounter. But you're never going to be exactly at 298 K. So, and oftentimes, in some cases, you're going to be far from 298 K. So what do you do in that case? You have to get a new table or something? Find a table that's at the temperature you want? No, you can correct for changes in temperature away from the table temperature. How do we do that? Well, first of all, we're going to calculate the table values at 298K. And then we're going to use this logic that is down in this diagram here to calculate a correction for the fact that we're not at 298K. How do we do that? It turns out that we know enough already to understand in rigorous detail how to do that correction. Let's see how we do it. Here's our chemical reaction. It's a generic chemical reaction in this case, right? A times species A plus B times species B goes to C times species C plus D times D moles of species D. That's all happening at some temperature, and we are assuming for the moment that that's not 298K, and that's the actual path that's taking place. And we want the delta H and delta S for that, but what we have from the tables are the values at 298K. What we need to do is take our reactants from our true temperature here to the 298K value, carry out the reaction at 298K, then we can use the tables, right? And then take our products back up to the temperature that we really want. Why is that valid, right? Why can we change this path that we're following here is not the true path. Why can we do that? Well, because delta S and delta H and all the quantities we're going to calculate this way are state functions. They don't care about the path. When we're changing the path like that, we're not going to change the final value, so we're free to choose any path we like. This is a particularly nice one, but it's not the only one we could choose. If we wanted to choose some other even more complicated path with extra steps in there, it won't make any difference. We'll get the same answer anyway. This particular path is chosen because it makes use of these table values, which is actually necessary. I don't know of any way to do these calculations without using the table values. So what will the delta H then be if we're going by this path? That will be the following. The delta H for going by our calculation path here will be the delta H for this step plus the delta H for that step plus the delta H for that step, and that will be the same as the delta H for the true path. So delta H sub 1 here is this step. Delta H, with a little symbol here that means standard state, is the delta H for the table, and then delta H sub 2 is the return to, that's delta H2 for the return to the correct temperature. So what we need is these two delta H's, and we know that the delta H is equal to the QP. This is all under constant pressure, constant temperature conditions. And a QP is equal to, at constant pressure, right, is equal to a heat capacity at constant pressure times the temperature change, assuming that the heat capacity doesn't change over the course of the temperature rise, which is good for, delta T's of around 50 degrees or smaller. If you're bigger than about 50 degrees, then the formulas I'm writing here, the idea will be the same. This path will still work. But this formula here, which assumes a constant heat capacity, starts to break down because the heat capacity starts to vary with temperature, and you have to do something more elaborate. You got to use the integrals that we talked about earlier. All right, so what's the heat capacity for this case? Well, it's going to be the total heat capacity for delta H1. It's the total heat capacity of the reactants, right, which is A moles of the molar heat capacity for substance A plus B moles of the molar heat capacity for substance B. So that's our total heat capacity on the reactant side times delta T. Notice that the final temperature for this step up here, this step right here, starts at temperature T and ends at temperature T0, the table temperature, usually 298 here. And so the delta T is, where is it? Here it is actually T0 minus T, right? And now I've reversed it to be T minus T0 and put a minus sign in here. So that's a little bit of a subtlety to notice. And then delta H2 is the same thing, but for the products now rather than the reactants, so it's C moles times the molar heat capacity for C plus D moles times the molar heat capacity for D. And now the final temperature for that third step is the actual temperature minus the initial temperature, which is the table temperature in this case. So it's T minus T0 already without a minus sign. Putting these things all together, we get that the new delta H at the new temperature is equal to the delta H at the table temperature times a quantity that I've called delta Cp. It's routinely called delta Cp. That isn't just my name for it. It's the heat capacity change for the reaction times the temperature change, whatever that may be, T minus T0. Notice it's the actual temperature minus the table temperature. What is this delta Cp? Well, it is the same thing that we've been seeing over and over already. It's the total heat capacity for the products minus the total heat capacity for the reactants. So it's products minus reactants weighted by stoichiometric coefficients, or to make it a little shorter, products minus reactants WBSC. We're going to see that over and over again. Actually, we might not see it that much after this, since this is the part of the class where you see it most often. But this business of products minus reactants weighted by stoichiometric coefficients, that's, well, you've been seeing that for a long time already, so it's probably familiar, but we'll see it again over and over in this class too. All right, so that's the expression. This is Kirchhoff's Law 1 for how to correct a table calculation, a table-based calculation for the fact that you're not at the standard temperature. What about entropy? Well, it's the same logic. The delta S overall going around the long path is going to be the delta S for the first step, the delta S for the tables, and the delta S for the second step. So this is, yeah. And the only difference is that the delta S contribution from delta S1 and delta S2 are a little different. The delta S1 is going to be the entropy change due to a temperature change for each of the reactant species. And that's going to be the number of moles. Oops, I should put a bar on those. Those are all molar heat capacities. Bars mean molar here. So the number of moles of A times the heat capacity for substance A times the change in, times the logarithm of the final temperature over the initial temperature, which is T0 over T for this step. And that's the total heat capacity for the whole set of all reactants, with a minus sign because I've changed this logarithm to T over T0 now, rather than T0 over T. And delta S2 is the same thing except for the products, and then logarithm of T over T0 for the product step. For the third step, T is the final temperature and T0 is the initial temperature, right? So putting all that together, we get that the overall delta S at a temperature not the table temperature is the table value plus again delta Cp, the same delta Cp, now times log of T over T0. So it's very similar. The two this is Kirchhoff's Law 2, as I've called it. The two Kirchhoff laws are very similar. There's just a small difference here at the end, right? Delta T for delta H and log T over T0 for delta S. All right. Just a couple more comments before we do an example down here. Yeah, first of all, this quantity delta Cp, the heat capacity change, is the change in the heat capacity for the products minus the heat capacity for the reactants, and it's usually a fairly small quantity. And the reason is that you aren't changing the number of atoms in the system. You're only changing the way the atoms are bonded to each other. And that usually doesn't have a huge, I mean, there is a change, it's not zero, but it doesn't have a huge effect on the heat capacity overall. And since this delta Cp is a small quantity, that means that the changes in delta S and delta H are usually also fairly small, even when the temperature change is rather large. And for that reason, a lot of times people neglect these correction terms over here and just go with the crude approximation of assuming that even though you're not at the table temperature, the delta H or delta S is pretty close to the table temperature. And that's good if your temperature difference isn't too big from the table, and that's going to be true if you're close to room temperature, which you mostly are. If you're far from room temperature, though, the corrections can start to be significant. When we do the example down below, we'll get a feeling for how big these corrections are. All right, so let's do that example now. Here's our example. We have, well, it's our water-forming reaction. 2H2 plus O2 goes to 2H2O. Here are the table values, and notice I've included heat capacity values here. The kinds of tables you see in a freshman chemistry book usually don't include these heat capacity values because you don't do these kinds of Kirchhoff calculations in freshman chemistry, but in a lot of thermodynamic tables you will see these heat capacities listed along with the delta H and S values and sometimes a delta G value, often a delta G value as well. So here are the values for H, here are the values for O, here are the values for water, and notice, oops, that is a mistake. That should be gas. These values are actually for the gas phase. I just wrote that liquid there, and that's wrong. And we're saying that this reaction is taking place at 350 K, not at 200. So these are the values at 298, and we want the values at 350 K. So first of all, let's calculate the table delta H's. Delta H of reaction is the usual rule, 2 times the water. And now notice the delta H's for hydrogen and for oxygen are 0. I think people are familiar with that. It's because the reference state for the table for delta H isn't absolute 0. It's the elements in their most stable state at the table temperature. And these are already elements, right? So they're the same thing as the reference value, which means there's no change from the reference value, which means you get 0. That's convenient. That makes a lot of these calculations easier, right? All right, so, oops, I don't want that. We get minus 483.66 for the delta H of reaction. What does that tell us? Well, first of all, it's negative. Why is it negative? Because the system, this is a delta H for the system, right? The system lost energy because the bonds on the product side are a lot stronger on net than the bonds that were broken on the reactant side, which means that in order for these water molecules to form at all, a lot of that energy, that bonding energy, was released into the surroundings, and that's the delta H. That's the negative sign on the delta H. It's also a big quantity, and in general, as we've seen above, and as probably people know from other classes, a negative delta H isn't enough to guarantee that the reactant will go, that the reaction is spontaneous. But it's a tendency. Things with negative delta H's, especially large negative delta H's, almost always are spontaneous because that's such a big contribution to the delta G change. And it's the delta G change that actually does predict whether the reaction will be spontaneous or not, as we've seen above already a little bit. All right, delta S now, calculated using the absolute third law entropies, is minus 88.8. It's also a negative sign. That's because, mostly, I mean, there are other reasons too, but mostly it's because there's 2 moles on this side, there's 3 moles on that side. We lost a mole of rotations and a mole of translations in going from the reactants to the products. It's a fairly big number too, as entropies of reaction go. That's not a huge one, but a good size one. And then finally, the delta Cp is the heat capacity, which is pretty large for water here, minus the heat capacity for oxygen, minus 2 times the heat capacity for hydrogen. That's all these numbers. And that turns out to be negative 2. Why negative in this case? Well, if you start looking at where energy can be stored in these initial reactants versus where energy can be stored in the products, Well, basically it boils down to there's 3 moles on this side and only 2 moles on that side too. So there's more translations and rotations that you can store energy in on this side than there are on that side. There's more vibrations on this side, and it turns out for heat capacity, vibrations are more important than they are for entropy. But even so, we're getting a negative value, and that makes sense because we're losing mole numbers in doing this chemical reaction. That means we can plug now into our Kirchhoff law. Delta H at 350 is going to be delta H at 298 times this delta Cp, this guy, times delta T, which is 350 minus 298, which is 51.85. Doing the arithmetic, we get 484 minus 484.68. Let's compare that to the uncorrected value. That was 483.68. You can see the correction is only about 1 kilojoule per mole on top of, getting close to 500 kilojoules per mole. So it's only about 0.5% correction. Still, in a lot of situations, 1 kilojoule per mole like this would be significant. The reason it isn't so significant in this case is that this is an extremely exothermic reaction. There's already a ton of heat being released. And now what this is saying is that when the heat capacity effects or the temperature change effects are being accounted for, it's even a little bit more exothermic, but not by a great amount. All right, now for delta S, the same thing. We use our formula, delta S from the tables, delta Cp, log T over T0. That T over T0 is 350 over 298. And I didn't write out what this correction is by itself, but you can see it's gone up by about 3 joules per K. That's a bigger correction. That's about a 3% correction, a little over a 3% correction actually, to the delta S. So none of these corrections is huge, at least for this reaction. There are other cases where it's more important. You can probably find edge cases where the correction actually changes the sign of the delta S or even the delta H, but that didn't happen in this case. And that is it for this lecture. We'll take up the next topic in the next lecture.